We will start very soon. We'll just allow another 1 or 2 minutes for people to join in. So while we are waiting, let me just say that we will have recorded presentations of myself, Professor Venkat, who is already logged in, and also Dr. Vipul Mann. And then after that, we will have discussion. So please keep your questions, and you can put your questions on the chat box, and we will read them out. Or during the discussions, you can raise your hand, and we will ask you to tell your question. There will also be, during the presentation, a questionnaire started, and you feel free to fill out the questionnaire whenever you can. It will be very important for us because then we can see how to improve future webinars. With this introduction, I will not wait anymore since we have almost a 3-hour program. So I will start part 1, which is my presentation. Please start the video. Hello, everyone. I'm Rafiqul Gani. I will start this webinar with part 1. But first of all, wherever you are, good morning, good day, good afternoon, good evening, good night. Thank you for joining this webinar, and welcome to this webinar. As I said, I will start with part 1, where I will introduce the methods for process synthesis design innovation with emphasis on the domain knowledge. The first thing I want to talk about is problem definitions. Here, say that we know the raw materials that we would like to process in order to obtain products with some specifications. Now, in some cases, the chemicals that come in and go out are the same. There will not be any reaction. It will be only a separation process. Or when the chemicals that come in and go out are not the same, then there would be some reactions or conversions of the raw materials. So this is the basic definition of the problem that we want to solve. We want to know the process flow sheet. We want to know its design. We want to know whether further, more better processes could be found. And I will define more clearly or more details what is the process synthesis problem. The process synthesis problem is that we have some raw materials that we can see on the left, RM1, RM2, and we want to process this to obtain products on the right, which can be P1, P2, P3. And then in the middle, we need some operations that will convert or process the raw materials to the products. And those operations can be different operations that you see on the left: distillation columns, heat exchangers, pumps, reactors, and so on. So the synthesis problem is which are the steps that are needed, and for every step, which operations are needed, as highlighted on the diagram of the network. Once we have the flow sheet, which is defined by the highlighted boxes, we have a process flow sheet, but we do not have the design of the operations in the process flow sheet. That means in a distillation column, do we have the number of stages, the feed location, etc.? In a reactor, what kind of reactor, the reactor conditions? In the heat exchangers, what kind of heat exchangers, the design of them? All these details need to be filled out. Now, the design also needs to be such that we have an optimal process flow sheet with respect to cost, with respect to other constraints like sustainability, safety, and so on. At this point, then we have a not only a process flow sheet, but also an optimal process flow sheet satisfying certain constraints. Now, is that enough? I would say it is not enough. We should try to look at more sustainable solutions. And here, by sustainable solutions, we mean that compared to the reference, can we find alternatives that are better in terms of energy, in terms of carbon footprint, in terms of operations, and so on. And if we can find them, then that is the final innovative process flow sheet that we are looking for, and that would be, by definition, more sustainable solutions compared to the reference that we have at the end of the design. So this is the problem we want to solve. Synthesis design innovation, and we will call it sustainable process design. What are the methods by which we can obtain them? The first one we will talk about is the evolutionary method. This is the method developed by Professor Douglas, and he wrote about it in his book, Conceptual Design of Chemical Processes. It has been used by many people and also in industry. The basic idea of this method is it's a rule-based expert system. Expert asks question, user answers the question. Based on the answers, expert recommends the next step, and gradually a flow sheet is evolved. I'm not going to show too much or discuss too much this method, but if any interested participant can contact us, and I can send several detailed worked out examples. Basically, the method is broken down into several levels, and at different levels, different parts of the process synthesis design issues are fixed, like is it a batch or continuous process? Are there recycles? What are the separation system? And so on. In summary, we can say that method needs a lot of data, a lot of knowledge, and also some computational tools that can be very simple ones, as given in the book, Douglas's book, but we can also use more detailed computational tools that will generate the data that is needed. The method is rule-based and generates a process flow sheet. There is no guarantee on optimality. The advantage is it's simple and easy to apply, and that's why it has been applied in many places. And the success depends on the expert knowledge of user and availability of necessary data and tools. At this point, I want to introduce a problem to you. Where we can see in the figure on the right, we have some raw material. We do not know what raw material. It comes into the reactor, and a reactor effluent goes out. Can we autocomplete this flow sheet? Just think about it, and I will come back to this later in my lecture. And I go to the next method. The next method is superstructure-based optimization. So instead of one flow sheet, we want to find all possible flow sheets and also the optimal flow sheet. So here we need a superstructure, and two of the issues in superstructure is concept of processing steps or tasks that needs to be performed, and the number of intervals or techniques available for each task. The first issue is what is a processing step and how many processing steps are needed. So if we want to go from the raw materials on the left to the products on the right, how many steps are needed, or how many operations are needed to be performed to process the raw materials to the products. So that's the first issue. The second issue is for each processing step, how many intervals, how many alternatives are there? If we can fill these two questions with all the information, we will end up with a superstructure, as you can see, in a simplified form. Another important issue is once we have the superstructure, we need, in order to do any calculations, we need models so that we can do not only just mass energy balance, design calculations, whatever. So what is the model for each of those boxes that you see in red and green and blue. We need models for each of the intervals or techniques. We need to derive them, or we can have them in a library. We have developed a generic, what we call a generic process interval model, where each interval can have operations like mixing, reaction, different kinds of separation. And in the library, we will have in the background different versions of those kind of models. Now, the interval can have all of these operations, or none of these operations, or a combination of those. So in principle, it could be a network within a network. But if we have the models of different complexity, we collect all the model equations for each of the intervals, then we will have the full model for the superstructure. Once we have that, we can say that we add an objective function that can have different terms: cost, specifications, sustainability criteria, health, safety criteria, and so on. And then we have the process model and the specifications on the products. We have constraints on the equipment and material. We have constraints on the combinations between intervals. Yeah. And this then represents a general problem, which can have different forms depending on the model we use and the problem we want to solve. So we can have linear programming, nonlinear programming, mixed integer linear programming, MI and LP. If we do not have an objective function and only the process model, we can also have just process simulation of different types. So once we have those model equations to represent the entire superstructure, we need a solver to solve those equations. And the solver will depend on what kind of problem we are solving and the problem complexity. The number of equations can be as little as 6 linear equations or as large as 6 million highly nonlinear equations. So what we need is also, in addition to the solver, a solution strategy. And all of these can be put into a computer-aided framework where we have a tool which will help to create a superstructure, which will help to retrieve the models from a model library and have the superstructure model, which will then formulate the problem that we want to solve and call the solver. And before calling the solver, we need to provide data, and in the form of model parameters as well as input data that can come from a database, and then we use the solution strategy to get the solution. This sounds quite easy, but some problems can be solved. But the kind of problem we wanted to solve, synthesis, design, analysis, innovation, is quite complex, can be quite large. We need a decomposition-based strategy to solve the problem. Summarize, for this method, we need a tool to create the superstructure that needs availability of data and knowledge. We need to evaluate the flowsheet that needs models, and size and complexity is an issue. And then we need to determine the optimal flowsheet. What you see in the figure below is the superstructure for the HDA process that we will discuss quite a lot in this presentation. And for this superstructure, there are 421 feasible flowsheet alternatives. Can we evaluate all of them simultaneously? It can be difficult. We prefer to do this in a decomposition manner, that is, break down the problem into smaller subproblems and solve them in a specific order. This brings me to the final method that we are going to discuss in more detail. This is the domain knowledge-based hybrid AI method for synthesis, design, analysis, innovation, giving us sustainable process design. So let's look at some of the concepts, workflow, and data flow. The method is based on thermodynamics and physical insights, especially for the chemical process synthesis or any process synthesis. Then use of extension of these insights plus some domain knowledge for the process design part. Here we also use reverse engineering, and then additional domain knowledge and more insights help us with process intensification. I'm going to also revisit representation of the process flow sheet, superstructure flow sheets,
anything else?
sustainable process design with
and a
respect to
bowl.
synthesis
Who
design
needs anything
analysis
else?
issues, sustainable process design with respect to innovation issues. So first, some concepts, flow sheet representation with the eSFILES. And here we can see that just like a chemical has a chemical name, for a chemical process, we propose to have a process name. Chemical has a formula with respect to the atoms present. The process will have a formula with respect to the process atoms present. And PA indicates here at process atom. The I in front indicates it is an input process atom. R, FL, DL, GM indicates they are operation process atoms. O indicates output process atom. And the numbers 2 indicate how many they are, just like in a chemical formula. And once we know the formula, we can write, in the case of a chemical, the SMILES string. In the case of a chemical process, we can write the eSFILES string. And once we have these, we can also draw the molecular structure in the case of a chemical and draw the chemical process flowsheet structure in the case of a chemical process. Note that this drawing is not just a picture. It has important information in terms of the atoms present in the chemical or the process and the bonds that connect them, and which chemical and which atom are very important here. So with this background, let me show you how we will use the concept of process atoms. We have a number of process atoms. We have a library of process atoms where you can see different types on the screen. We combine them, get a flow sheet. We have the formula for the process, and we have the eSFILES for the process. I'm not going to discuss more on these now, because in the third lecture, Dr. Vipul Mann will give you all the details of the grammar and the syntax and so on. So now with this concept, let's look at workflow for sustainable process design. We have 12 hierarchical steps. The first 2 are related to problem definition and problem analysis. Then the next 3 is related to synthesis. The next 2 are related to the process design and analysis, and the last one in innovation. But note that all of these have many sub-steps which are not listed here. For example, the one step of 10, 11, 12 of process innovation, for each type, each sub-step of these have a lot of other algorithms and steps. But we'll start with one by one, the problem definition. But before that, let me also point out that this method is knowledge-based intelligent system. It does not ask questions like the evolutionary method to make any decisions. It generates the data and guides the user through the workflow steps of different algorithms. It's the user who is in charge. It's not an automated system, but it's an interactive system. So the first step, as we talked about before, we need to tell what are the input material, that is the raw materials coming in, what are the products one would like to have to process that. information about all the input and output in terms of purity, in terms of purity of the product, in terms of impurity coming in with the reactants. In this case, and we are going to use the HDA process as example to highlight all the different steps. So in the HDA process, we have two streams coming in. There are two reactions taking place. We have the kinetic data, we have the product specifications. And because the chemicals coming in are not the same as chemicals going out, it's obvious that we have reaction. In each of these steps, whenever you see the box with available in ProCFD software, it means our software ProCFD for sustainable process design has all these steps included in the software. And we use some kind of symbolic AI that Professor Venkatasubramanian will also talk about. So we provide a guideline to the user to define the problem. And once the user has defined the problem, we will get to know that the process has reaction. The reaction kinetic information is given, and we will know that because the reaction is not 100% converted in terms of raw materials, so there will be reactants that need to be recovered and recycled. And the total number of chemicals coming out of the reactor will be also known, and high purity separations will be necessary. These are the information that we will get. Also, the user, in this case, will have to provide the reaction. We are developing a reaction database, but until that time, the user has to give the reaction, and if the atomic balance does not satisfy, the user will have to provide the reaction such that the atomic balance is satisfied. Otherwise, it will not proceed. Once we have the step one, now know all the information. The next step is knowing this information and generating additional information in terms of retrieving data of the chemicals of the process, retrieving or calculating property calculations of binary mixtures, and many other similar calculations, but not actually process calculations, because we do not know the process at this moment. We know the chemicals, and so we calculate the properties of chemicals, both pure and mixture, and from that, we will try to figure out with our tools what kind of separation or operations can be used to generate the flow sheet. So, and also we know that since hydrogen and methane are coming in together, it will be also going out together. And so even though we have 5 chemicals, we have 4 products. And because we have 4 products, then we will have minimum of 3 separation steps in the process. And because we have 5 chemicals, we have 10 binary pairs of chemicals. Each binary pair could indicate the key compounds in a separation. And if we know the properties of all these binary pairs, like what are the ratios of boiling point, melting point, vapor pressure at boiling point, and so on, it can indicate to us which type of separation would be feasible. Also, we take into account the driving forces, whether any binary pair forms an isotope or eutectic points, and so on. Based on these informations, we will be able to find out from our knowledge base a set of feasible separation techniques that could be used after the reaction. So next, we go to the step 3. Having all this information that I pointed out in the previous step, we will now have a list of the process atoms. We have 2 input atoms, 4 output atoms, 1 reactor atom. We could have added more reactor atoms if we had more reactor informations. We have identified 168 separation atoms and 2 purge atoms because there are 2 recycles. What are the 168 separation atoms? We have separation techniques for 4-compound separation, 3-compound separation, 2-compound separation, and for each of them, distillation could be one, membrane could be one, absorption could be one, crystallization could be one. So all those separation techniques are taken together and we have 168 separation atoms. What is the next step? Next step is to generate the flow sheet. Having all this information, the problem is now, how many ways can we assign the process atoms that we have to the 3 downstream separation steps after the reactor atom? Note that the input atoms are at the start, the output atoms are at the end. So how many ways can we combine? And we have put in rules so that some redundant combinations are not used. So for example, if we have already decided a 4-compound separation, in the downstream part, we do not need to consider those 4-compound separations anymore. So like that, we can, even though there are 168 separation atoms that can, in principle, give us many flow sheet alternatives, but it's not a combinatorial explosion. And here are 2 examples. If we do not restrict the separation techniques that we can generate, now we will have 400 superstructure with 421 flow sheet alternatives. These are feasible theoretically, but we cannot calculate for all of them because for some of them, we know that we do not have the model parameters. For example, we may have several membrane-based separation atoms, but for some of them, the permeability data that would be needed are not there, or the absorption isotherms are not available. So if we remove them, and if we also see that the HDA example process is a hydrocarbon separation where there are no isotopes and no close boiling mixtures. So basically, a combination of flash and distillation are feasible there. So if we take only the flash and distillation, you see the superstructure below, which has 10 feasible alternatives, even though many more can be generated. So now let me give you a little bit of more concept with respect to extension of the eSFILES for superstructure. So let us say that we have a mixture ABCD that may be extracted from some seed or or from the ground, or is a reactor effluent. We need to separate these 4 compounds into 4 pure compounds. And let us say for illustrative purposes that these 4 compounds, no binary pair form isotopes, and they can be separated very efficiently by distillation. So we have a 4-compound separation, and we need minimum 3 steps. In the first step, we will make a 4-compound separation, and by distillation, only these 3 will be feasible. And the integer variable we have introduced now, these are binary integer variable. If it is 1, that is the path that will be taken. If it is 0, then it's not the path that will be taken. And the summation of these 3 binary variables will be 1. So in that case, going from the 4-compound to the 3-compound separation, or after the first separation step, we will only use one of these 3 alternatives. Note that the second alternative breaks the 4 compounds into 2 pairs of binary pairs. And the other ones reduces the 4-compound separation into 1 product and 3-compound separation. So in the next step, we have 3-compound separations. The middle one is bypassed because the separations involve 2 compounds. So we have these alternatives, and then the last one have 2-compound separations. That is the superstructure, and in each case, all the binary variable summation is 1, so we will only use one of them. So that's the first part of representing the superstructure in order to write the eSFILES or derive the eSFILES for the superstructure. Next step, we collect all this information and we put them into a SMILE string, just like the eSFILE string. So we have the input A, B, C, D. That's the input atom. Then Y1 indicates if it is 1, that is the process atom will be used. And the subscript K indicates one of the 3 that is available in step 1. Then in step 2, we have a J because there are 2 alternatives for some of the intervals. And then the K is which interval. So by adding the values of J and K for each of those intervals, we can generate from this eSFILE of the superstructure all the different flow sheets that are needed. But before I go there, let me also show the hypergraph for the superstructure. And again, with the integer variables and the values of J and K, we can generate any flow sheet from this superstructure. So now let's see, have the hypergraph, we have the S-files for the superstructure by giving values of J and K for every processing step, and then having a table with all the groups corresponding to J and K. We can then generate the eSFILES for any process flowsheet alternative. And this would be level 0, where it will be the flow diagram indicating how many chemicals are there, what kind of operations, how more information about which chemicals, which operations, more information in terms of additional information in terms of which type of operations, what is the model for that in the simple case, like simple mass and energy balance, more rigorous models. In each case, especially in level 2, levels 1, 2, and 3, there's input information, there is output information, and as we go higher in level, the amount of information increases. But it's both input and output information that is kept. And you will get more information about this also in the 3rd lecture by Dr. Vipul Mann. So if we go back to the HDA case, we have the superstructure, the simple superstructure, the 2 recycle candidates are highlighted. You can see the eSFILES of the superstructure, and 10 flowsheet alternatives are generated. Now the next question is, we have generated the flowsheet. How are we going to do the design? Should we design all of them and optimize all of them, or should we remove some redundant ones? For that, we need to evaluate these flowsheets. But we do not have the design, so we cannot do detailed simulation at this point. So what we have therefore developed is just like a chemical, we can use the structural information to calculate the property of a chemical. Here, we are going to use the structural information to calculate the properties of a flow sheet. And these properties of flow sheet could be energy consumption, carbon footprint, product recovery, product purity, environmental impact, and so on. And the equation you see is similar to group contribution type of model for property calculation of a molecule. We know the groups, or we know the atoms and their contributions, so we can calculate the property. And what you see on the screen in the table is all the 10 flow sheets that we have generated. For the HDA example, if we take the energy index, we see that there are 2 which are very good with respect to energy index. The lower, the better. And the last 4 are not very good. So we can highlight, or we can focus on the first 2 or the first 6 if we want, and ignore the last 4. So for these, let's say, the small number which are promising, we will do the detailed design. And then for each of those flow sheet, as I mentioned before, we have the level 1 information. We will add the level 2 information with the simple models. We will add the level 3 information with the more detailed models, and more information about this will be given by Dr. Vipul Mann in lecture 3. So I will skip more information. But note that from level 1, level 2, level 3, we can connect to different calculators, simulators, to do the simulations and pass the values to us. HDA process was a simple process in terms of separations, because there were no isotopes, there were no gas absorption required, and so the flow sheet was simpler and did not require some complex decisions. But in many chemical processes, we do have isotopes, gas separation. So we have introduced the concept of process groups, which is a combination of atoms, and there is an internal recycle within them. So like a solvent-based extraction that you can see, solvent-based absorption, not solvent-based, but pressure swing distillation. All of them have a recycle, but which is within the process group. As far as the process atoms are concerned, we have 2 process atoms. It can be 2 or more process atoms that defines a group, but we are defining these groups in such a way that the recycle is within it. And it has the same concept like a ring compound, aromatic ring or a naphthenic ring compound would be similar to this kind of process groups. And how can we use these process groups? We have if we take the methyl acetate process, where there is a reactor followed by membrane separation distillation and a pressure swing distillation. We represent the 2 columns in the pressure swing distillation by a process group. And here is the superstructure, smiles for it, and different alternatives we can generate. If you look at the green part, pressure swing distillation is possible, solvent-based extraction is possible, and for different solvents, there will be different process groups. So we can generate a large number of alternatives, but note that the process group recycle is not affecting the other parts of the process flow sheet. So it's actually simpler to use and more efficient to do calculations. Another example, the MTBE, where there is absorption followed by solvent recovery. And in the same way, we can generate all the information we need. And again, it's a much better way of representing more complex flow sheets. In the presentation by Dr. Vipul Mann, he will also show an example where we have 2 reactors in the process followed by separations. So there will be a process group and representing one part of the process, and another part is just the process atoms. So things like that also can be done. So at the end of step 7, we have a flow sheet, 1 or more very promising flow sheets, and we can evaluate them So here now we will do the analysis of cost, sustainability, LCA, safety, and many more. And by doing that, we will identify opportunities for improvement. This can be, for example, integration of hot and cold streams with respect to heat exchange. We could have done that already before. We can also do it here. We can also find out information like one of the distillation column is using a lot of the energy. There is some unacceptable release of compounds in a purge stream, like benzene going out in the purge stream, high pressure flow of gases, and so on. Then once we have identified them, we can set the targets for improvement, and then by optimization, by adding more information, we can find alternatives that are better than the reference. And then by definition, any that matches those are more sustainable than the reference. So that will be at the end of 9, we will have the targets and the analysis and the reference process. And in 10 to 12, we will do the innovation. And as I said, based on the targets, we will try to find a flow sheet that is better. In the case of the HDA, we do the heat integration and optimization, and we find a more sustainable design. In addition to optimization and integration, we could have also done intensification or other hybrid schemes. And would they be feasible or not? Should we use trial and error way to check whether we can use reactive distillation or dividing wall column or hybrid distillation membrane to improve this process? In order to do this, we have developed a rule-based method where we ask 7 questions in each case. If the answers to each of them is yes, then there would be a part of reaction followed by separation that could be replaced by distillation, or 2 adjacent distillation columns replaced by dividing wall column, or a distillation column could be membrane could be added to the distillation like a retrofit to improve the energy. So all of this can be done, but we do not do trial and error. If the answers to all the 7 questions is yes, then definitely they will be feasible. So here are some examples. We have the methyl acetate process that can be converted to a reactive distillation, dioxylane process that can be converted to reactive distillation as well as dividing wall column, separation process of hydrocarbons coming from a petrochemical complex that can be converted to dividing wall column and hybrid separation. So here is the example of the hydrocarbon separation. This is coming from an actual industrial problem. The first 2 columns are converted into a dividing wall column. Last column is membrane is added, and this alternative gives nearly 40% improvement on the original. And we have now the corresponding process groups also, and a corresponding model for them. Similarly, for the methyl acetate example, the flow sheet is converted to a reactive distillation with improvement also at least of 20%. The dioxylane process, we have the reactor plus the distillation column replaced by a reactive distillation column. The distillation columns replaced by a dividing wall column, and they're combined together to form a reactive dividing wall column. And I come back to the question of, we have some raw material coming into the reactor. The effluent is coming out of the reactor going into an absorber. Can we autocomplete this flow sheet? Does it make any sense to do it? And what I would say is that it doesn't make any sense to do auto-completion without a context. We need to know what is the reaction. We need to know how many compounds are coming out, so we can find out which of the generated flow sheets would be feasible or not. So auto-completion without context would be just generating all kinds of flow sheets. Some of them would be feasible, others will not be. By putting a constraint or a context, we screen the generated flow sheets to find out which are the feasible. This will be discussed in more detail by Professor Venkatasubramanian in his second lecture, but we'll just show the same flow sheets and raise the same questions. Each of them are correct. It could be all of them are wrong. It could be one of them is correct because of the reactions that will take place. Summary of this method is we have an intelligent, flexible, consistent process synthesis design innovation method. We use hybrid AI with machine learning and domain knowledge wherever necessary, allow systematic solution of related problems by effective or efficient management of the complexity. We use computers to speed up. We use domain knowledge to define the problem at every step. We use AI together with HI, which is, for me, human intelligence, because we have to select the AI, we have to apply the AI, we have to train the AI, so human intelligence should not be forgotten. To reduce the complexity, we use appropriate numerical methods plus ML with HL, that is human learning. We are the one who needs to apply the machine learning. We are the ones who need to train the machine learning. So we also need some human learning there to efficiently and reliably solve the problem. It is important to understand the system and the problem to be solved for the system. Finally, you have seen a lot of red blocks which says available in ProCFD software. Here is the ProCFD software. This includes the workflow for the sustainable process design, and it is connecting with a large number of methods and tools. It is organized in such a way that the blue boxes surrounding it are the different steps, different methods that are needed, which are the blue boxes. And each of those blue boxes need a number of tools, computational tools, AI tools, machine learning tools. These are on the outside, which are the green boxes. Altogether, is this software which is continuously being developed and improved. Finally, some perspectives. Even though much progress has been made, there are still many issues that need to be addressed to establish the scope and significance of the method that I have shown you. And additional development means widening the scope and significance. So we can solve many problems, but we want to widen the scope and significance. Some extensions, like how to include the vast and available domain knowledge into the algorithms, methods with associated tools, how to transfer the relevant data from one application or problem to another, how to improve and add new models of different layers. So a modeling tool is very important, and we are developing those modeling tools. How to guide the user to make intelligent decisions and avoid infeasible designs. How to guide the user to make intelligent decisions and avoid infeasible designs as early as possible. Combination of domain knowledge with data is necessary to develop correct and consistent methods. We want to use all available tools where and when necessary. We want to generate alternatives, but generation of alternatives without context is not an issue. It's quite easy. But we need to add the screening so that we generate alternatives that are feasible. And it is necessary to understand the system and the associated problems. with this, I want to finish here. And after me, Professor Venkatasubramanian will start, and he will give part 2 with background and overview on AI and hybrid AI. And then that will be followed by Dr. Vipul Mann, where he will talk and give more details of the eSFILES and the generation of alternatives and the hypergraphs and so on. And after that, we will have a discussion. So thank you very much. Okay, so before Professor Venkatasubramanian's recorded video is started, Venkat, do you want to say something before it started?
Good morning, everyone from New York, and thank you all for joining us. And I look forward to the discussion at the end of this series of presentations. Thank you, Rafiq.
Okay, just remember that questionnaires would be available from now on. Please fill out the questionnaires. The Thai team, please start Professor Venkat's presentation.
Hello, everyone. This is Venkat Venkatasubramanian. I'm delighted that you're all joining us for these presentations. My objective is to give you a broad overview of AI and machine learning and how these techniques fit in chemical engineering applications. So I'm kind of the bridge between what Professor Gani talked about and what Dr. Vipul Mann is going to present next. So what is AI? Well, artificial intelligence is the study of how to make computers do things at which, at the moment, people are better. Now, when this definition was proposed some 40 years ago, it seemed like a far-fetched goal because computers weren't that powerful. And people seemed to be extremely good at lots of things. But things have changed in the intervening 40 years, particularly in the last 5 years with the arrival of LLMs. We know that computers are routinely overtaking people in many, many aspects of human endeavor. So AI is not all that new in chemical engineering. I trace it back by about 40 years, and I classify these 40 years into 3 broad phases. One started in the 80s, and the second phase started in the 90s, and the current phase we are living through. Let me give you a quick overview of these things. Now, I'm going to skip over the technical details. If you are interested in the details, please read this paper that I published some 5 years ago. And so today is sort of a very quick overview of what has happened in the last 40 years and where we go from here. So brief history of AI. The origins go back to the 30s and 40s when mathematicians, particularly logicians, started playing around with the idea that some aspects of reasoning could be formalized, which means they can be automated. And then they built upon this idea in the 40s and 50s, and Turing came along and proposed his Turing machine in the 50s, and also the famous Turing test. And so all these things are ideas about the link between the formalization of reasoning and computation, and that abstract concept of computation as symbol processing, which can be automated, hence computers. AI was born at this conference in mathematics at Dartmouth in 1956, and the name artificial intelligence was given at the time. And the initial focus was on symbolic AI because it all came out of symbolic logic. And in the 60s through 90s, AI people tried to get computers to do vision, natural language processing, robotics. Expert systems arrived at the time, various AI languages called Lisp and its dialects arrived. And from 1990 onwards, the field shifted towards machine learning, particularly neural networks-based learning, with the rediscovery of the backpropagation algorithm in 1986 by Geoffrey Hinton and company. And so the focus shifted to data-driven AI, and ideas like autoencoder, deep neural nets were proposed in the 90s, reinforcement learning, etc. And then the most recent exciting innovation is transformers, which is behind all the large language models. Okay, so in phase one, which is what I call as the expert systems era, here the idea was to develop computer systems that mimicked human expert reasoning. And the key ideas were structuring these systems in this form, a knowledge-based inference engine and the user interface. And the knowledge base contained domain-specific knowledge, which was represented in the form of if-then rules and semantic networks. And this separation of domain knowledge from inference was a key idea, which gave rise to flexible execution order of the program. So this all happened in the late 70s and early 80s in computer science. And then immediately these were adopted by chemical engineers in the early 80s. The earliest expert system was developed at Carnegie Mellon by Art Westerberg and his graduate student, Rene Benyaris Alcantara, a good friend of mine who is now a professor of chemical engineering at Oxford. So Rene did this confined work for his master's thesis and decade for his PhD. And others also started looking into AI-based approaches. George Stephanopoulos at MIT started his AI work around that time with this focus on design, process design. And Mark Kramer again at MIT on fault diagnosis, Jim Davis at Ohio State at that time on design, and myself at Columbia on fault diagnosis. So that was phase one. Then in phase two, as I mentioned, neural networks was the focus. And that's because, expert system development had certain drawbacks. They required too much time, effort, and specialized expertise. And so as a result, they did not scale well for industrial applications. And so people were looking at other paradigms, and neural networks arrived, particularly with the rediscovery of the backpropagation algorithm, where you simply had to show the data to the neural network and it automatically learned the association between these patterns by adjusting the weights. So that's where the backprop comes in. And it's a bottom-up strategy, and where the system automatically learned the patterns, which made system development a lot easier. So immediately people started applying these things for nonlinear function approximation problems as well as classification problems. And in chemical engineering, lots of applications in process control, fault diagnosis, and property prediction, and so on. And then we entered phase three, which I call as the data science era. And that started roughly 15 to 20 years ago, but really picked up speed in the last 10 years. And the key ideas here are the convolutional or the deep neural networks, as shown here on the right-hand side for a vision problem, reinforcement learning, and statistical machine learning. And what these techniques enabled was to be able to do hierarchical feature extraction, as you can see here, which is what is needed for complex visual perception. These ideas were important, but not all that new. As I mentioned, many of these algorithms and ideas were proposed in the 90s. We simply couldn't use them that much because we didn't have the computing power or the data. So what is really new now are data, GPU, and software, more or less in that order of importance. And this is why now we have Watson, Siri, Alexa, AlphaGos, LLMs, and so on. Now, despite all this exciting progress in AI, there are still some really troubling questions or troubling issues still remain unresolved. For example, a self-driving car shown here in the picture may do a great job driving through the streets of Manhattan, better than most New York drivers, including myself, for example. But does it really know and understand the following concepts such as momentum, acceleration, force, Newton's second law, F equals ma, and so on, as we do, as people do? My claim is they don't. Their behavior is like that of what you see in these National Geographic videos, where a cheetah is chasing a gazelle. And both animals display a great mastery of the dynamics of the chase. But both are clueless about the underlying physics, which is classical mechanics, or the underlying math, which is calculus. So these animals have mastered their task in an operational way. They have an operational understanding. They know what to do, how to jump, how to run, how to chase, how to bob and weave, but they don't understand the deep principles. My claim is that current AI systems have achieved perhaps an animal-like mastery of their task without gaining a deep understanding as we do. Now, as a scientist, this is deeply troubling to me. And that's why in my lab, we've been working for the last 40 years in developing hybrid AI systems which are grounded in first principles, where we try to put in as much of the underlying physics, chemistry, and biology as possible, and not be purely a black box oriented data science kind of a model. So we develop first principles based models because I think that is the way to go in the long run, even though in the short run, machine learning data science has its uses. So it's also concerning to me as an engineer because mechanistic causal understanding is important in certain applications like diagnosis, control, and safety. For example, when Yelp makes a recommendation and you go to a restaurant with your date and you don't like the food, and then you lost perhaps a couple of hours and a couple of $100, and maybe your date is mad at you, but hopefully nobody died. Whereas in our domain, when things go wrong, the cost of a mistake can be potentially very high. When our chemical plants explode, people die. When planes crash, people die. So the cost of a mistake in movie recommendations and restaurant recommendations is low, whereas in certain domains such as chemical engineering, nuclear engineering, pharmaceutical engineering, aerospace engineering, mining engineering, and so on, the cost of a mistake could be potentially high. So we cannot simply trust black box models. We have to build first principles based hybrid AI models. So this brings us to the topic of hybrid AI, which is combining numeric AI, which is machine learning, with symbolic AI of the 60s, 70s, and 80s. And the benefits are the models are simpler because they are grounded in first principles. You need much less data to train them, and they are more reliable, and they offer you insights and explanations. So I'm going to give you 3 different applications as examples of how hybrid AI models can be developed and how they look like and so on. The first one is the flow sheet synthesis, which is what our presentation today is about. Professor Gani talked about it, and Dr. Vipul Mann is going to talk about it much more in the next presentation. So I won't spend much time on this because you're going to hear a lot about this in the next presentation. But I'll give you a quick flavor of how hybrid AI would look like in the context of flow sheet synthesis. But I'll spend more time on 2 other applications, which we won't elaborate, which is mechanistic model discovery from data and reaction prediction, and how hybrid AI systems look like in these applications. So now hybrid AI is going to look different in different applications. That is the idea. So that is the feeling, that's the message I'm going to leave you with and give you a sense of how these things can look different in different applications. So if you look at flow sheet synthesis, there's a lot of excitement about, autocomplete approach, like what LLMs do for flow sheet. completion. That is, given a partial flow sheet as shown here, can you automatically complete the rest? Now, in natural language, of course, this idea has been enormously successful. This is how ChatGPT, for example, converses with you. Based on what you have said, it guesses the next word. For example, if I were to say, I'm going to be home for, it's a reasonable guess to say a dinner or party or this weekend or summer and so on. So these are reasonable guesses. And even if you guessed wrong, you can still carry on the conversation by correcting yourself in the subsequent sentences. But such a procedure, will it work in highly technical domains such as flowsheet synthesis? Okay, for example, this partial flowsheet can be completed in many different ways. As shown here, there are 3 different options. There are many more options one can come up with. And which option makes sense depends on the underlying physics and chemistry or the process context. So without the contextual information here, just giving these 3 process equipment and saying, go complete the rest, it makes no sense because I can generate hundreds, sometimes even thousands of possibilities. And most of them are going to be useless without knowing the process context. For example, what is the reaction? Is it A going to B, or A going to B plus C, or A plus B going to C, and so on? Depending on these things, different flow ways this thing can be completed. So there is a mismatch of process knowledge and flow sheet. And the way to do this is not using purely data-driven AI, but you have to use the domain knowledge. That is the context and the underlying chemistry and physics related constraints and so on. And this is what we call as hybrid AI. And the domain knowledge is built in the form of an ontology, which I'll talk about in the next few slides. And then you combine it with machine learning techniques. So what is an ontology? Basically, ontology is the study of existence, as philosophers told us, but then computer scientists have a more practical view of this term. Ontology is the formal specification of concepts and relationships, basically because how do you represent knowledge in a computer? How do you formally structure it? And that is what ontology is about. And it has had a long history in its evolution. As I mentioned, in the 30s and 40s, knowledge representation started with ideas from symbolic logic. Then in the 60s, semantic networks came along. Then in the 70s, frames came along. And in the 80s, objects. And the most recent avatar of this long series of evolution is ontology. Now, web-driven software development also contributed to this development with object-oriented programming and so on. And nice thing about this ontological framework is it's grounded in first-order logic. So it's got some serious mathematical foundation. Which is the foundation for formal reasoning here. And so what do ontologies do for us? They help us create computer programs that can be easily created and shared, and the knowledge can be used again and again and again. So, and all these things make large-scale development a lot easier. Here is an example of an ontology. This is developed the example comes to us from pharmaceutical engineering domain. So where, excipient is a kind of a chemical that you put into a tablet, for example, and so it's a material. API is the active pharmaceutical ingredient, that's a chemical. That also is a material, and materials have compositions, they have properties. So organizing knowledge like this, typically in the form of a graph or a tree, and these things can be further developed, and this is what an ontology is in practical terms. And this thing which we have drawn here needs to be implemented in a computer as a program, as a code, and that's where the ontology language comes in. The web ontology language, OWL, is one of the most widely used languages for modeling, coding ontology. And the editor protege shown here is a way to work with OWL, and this was developed at Stanford a couple of decades ago. So here is an example of process ontology. You will see more about this in the next presentation. Vipul will talk about this. The right-hand side shows, for example, an ontology in pharmaceutical manufacturing. So you see materials, excipients, gases, impurities, and so on. How all these things are all related, connected. And this is on the left, you see a process ontology. For example, you see design that can A reactor could be a part of it, distillation column, and then flash and heat exchangers, and those things have their own components. So how to organize all these equipment and chemicals and concepts and so on in a structured, organized way so that they can be used in reasoning and decision making. That's what ontology is all about. And so, and we rely upon ontologies quite a bit in our work. Our group developed the first ontology for pharmaceutical engineering called POPE, Purdue Ontology for Pharmaceutical Engineering, that was developed some 15 years ago when I was at Purdue. And I've extended it now to the Columbia Ontology for Pharmaceutical Engineering, COPE. These things come from that work, and it's been used in a wide variety of applications. So you're going to hear more about them in Vipul's presentation. So you'll hear how Vipul uses these ontologies in connection with hypergraph, and which is a way of representing the flow sheet, a richer way of representing the flow sheet. And so you'll see all these things are combined in the next presentation in great detail. So I'm not going to go into them here now. Instead, I'm going to focus on the other two applications. But before I get there, using these things, by using the context, then by specifying the chemicals, for example, A, B, and C enter, and then A, B, C, D, E come out, and then D and E are recycled, knowing all these things immediately eliminate a lot of these flow sheets you might have considered otherwise, and the search space gets greatly reduced. And so instead of hundreds of possible flow sheets, you have only 10 to investigate. And these are the 10 which make sense given these conditions. And then you go on to create those things and then do the further analysis. And this is how Vipul is going to talk about next. So moving on to the second application, where I want to show you how hybrid AI is used, it's mechanistic model discovery. So here, the problem is, given some noisy data, can we automatically determine the underlying mathematical models and then explain those mathematical models by relating them to first principles based mechanisms? So this work, this is intelligent modeling assistant work that we are doing here at Columbia, has two components. The first half is the AI Darwin approach, is the AI Darwin system, and the second half is the MEGAN system, which stands for Mechanistic Explanation Generator. I won't have the time to talk about MEGAN much in this presentation. I'm going to focus on AI Darwin and show you how hybrid AI is used. But if you're interested in more of the details, please refer to the papers listed here. Now, as the name implies, AI Darwin uses genetic algorithm to discover evolutionary procedures to discover models. And so the goal here is to avoid functions like this. If you look at, this is actually an output from a symbolic regression system that fitted some data to this function. The error, of course, mean square error is very low. So the fit worked well. But to me, looking at the last term, exponential to the power of x1, which has an exponent, that is a red flag, because there is no process in physics or chemistry that will give rise to this kind of a model. So to me, even if the error is low and the fit is good, this model is suspect because the underlying physics and chemistry make no sense. So we designed a system, Darwin, where it cannot produce these kind of models. It can only produce models which we can relate to first principles physics and chemistry. So we created an elementary function library where only functions such as these shown here are allowed, because we can relate these things to fundamental physics and chemistry principles, and certain combinations of those things are shown here on the right-hand side. And so we use genetic operations to create new models, such as variable mutation here, or functional mutation shown there, or crossover operations for larger model combinations. And with these, AI Darwin will systematically identify mathematical models. So we tested it for a variety of chemical engineering applications. The true function is shown in the second column. For example, this function is to generate data and added noise, and fed the noisy data to AI Darwin to see whether it can identify the situation. As you can see, it did pretty well. Version more or less right. The constant is slightly different, and that is because of the noise. If we make the noise 0, then it discovers this constant to be exactly 20. And as you can see, even with that small difference, the error is pretty low. So it's a pretty good fit to the data. In the second example, you see that it's an exponential function, but you don't see an exponent here. However, you realize that if I expanded this exponential function as a Taylor series, then this resultant is very close to this one. So I essentially discovered the Taylor series expansion of the exponential function and retained only the first two terms because that's all it mattered. Even with that approximation, you can see the error, if the fit is good, the error is quite low. When it misses certain nonlinear functions such as this one, the fit is still quite good, as you can see, and it comes up with a reduced order model. So AI Darwin discovers the actual mathematical equations behind data, where the important thing here is it uses domain knowledge. Where is the domain knowledge? It is all in the library that we have put in. We allow only certain functions, and we can relate those things to fundamental physics and chemistry, and that's how this is a hybrid system. And the last hybrid AI example I want to show you is reaction prediction and retrosynthesis. And this is also the work of Vipul Mann, your presenter, the next presenter. So this was part of his thesis, but he's not going to talk about this. He's going to talk about the eSFILES work. And so I'm going to mention this as another example of hybrid AI. So here, the problem is, given the reactants and reagents, can you guess, can you predict what kind of products can be made? So in some sense, it's like a natural language processing problem. It's like a machine translation. That is, given a sentence in English, can you translate it to French, for example? And so Vipul approached this problem as an NLP, and except he made an important contribution by changing the representation. So instead of a purely smiles-based representation, he developed a more sophisticated, richer representation that captured the chemical and structural information. You'll see it in the next slide. And also he developed a special grammar, a context-free grammar, which captured the underlying chemistry. So these are the grammar rules, for example, which captures the structure and what kind of reactions take place, what kind of bond rearrangements and atom molecular rearrangements take place, and so on. So this is the grammar rules that Vipul developed. And here is an example of his representation. So propene, which we write it this way, in smiles, it looks like this, CC double bond C. As you can see, it's a nice, simple representation, but it misses a lot of the structural information, such as the branchings that are there. And so Vipul's representation is shown here. It's more involved. As you can see, it's more complicated, but then it's richer. It captures a lot of these structures. And as a result, it produces, it can impose a lot of the chemistry and physics constraints. And so it only produces molecules that are legal in chemistry. So it won't arbitrarily come up with structures which make no sense. Okay, so that's the benefit you buy. And then he uses the transformer architecture because we put in a lot of chemistry knowledge. His system uses fewer parameters, makes fewer invalid predictions, and captures a lot of the information correctly. So the evaluation metrics are, given a target and you made this prediction, there are three factors that are most important. One is the accuracy of the prediction, which is, did I get the target? If I didn't, my accuracy is 0. As you can see, in this case, it is 0. But then, is this a legally valid molecule? That is, will chemistry allow this molecule? Since Vipul developed this grammar to constrain the chemistry, he only creates molecules that are chemically feasible. Even if it is the wrong answer, it is a molecule that can exist in principle. And so here the syntactic validity is 1 because this molecule can exist in principle, except it's the wrong answer for this reaction. Similarity score is how similar is the product predicted to the target. And as you can see that it is actually quite similar because it has got this long chain. There's a long chain there. Then there is the double benzene ring connection, which is over there. Then that benzene is connected to this, and that is also here. What this is missing is these two benzenes. So as a result, the similarity score is fairly high, 0.74 on a scale of 0 to 1. It's pretty good because it is similar to that. So with this, Vipul trained his system on this US Patent Office database of nearly 1 million reactions. That's a standard one everyone uses to test their system. And then there is also a standard testing protocol. There are 80 reactions that were not part of the training, and they were used for testing the performance of the system. And these 80 reactions fall into 8 reaction templates with 10 each. And that is shown here in the x-axis in increasing order of complexity. So these reactions are simpler than these reactions. As you go in the right, the reactions get more and more difficult to predict. The y-axis is your accuracy of predictions. So what people have done was they've given these 80 reactions to human experts. These are, expert chemists. And they were given these reactants and reagents and asked to predict the product. And you can see their performance. For the simpler reactions, their performance is pretty good, 65% or so accuracy. And then as it got to be more and more difficult, the accuracy slips to more like 50%. And then as it gets harder, even below to 30% or so. Okay, so this is the human performance. Now, not just your average human, this is the expert human. These are all folks who are expert organic chemists. Well, how does our system do? Not bad, as it turns out. For the simpler reactions, it does about 20% better than the humans. It's in the range of about 80–85%. And for the moderately difficult cases, for reasons we don't fully understand, it does much better, nearly 100%. And then as the reactions get more and more complicated, its performance also slips and comes down to, but no worse than humans. So here is a system which does much better than humans in most cases, and at least as good as humans in the most difficult cases. And as you can see, the accuracy, overall accuracy is about 73%, which is pretty good. And the valid fraction, that is the chemicals it predicted, they're all valid chemicals because Vipul's grammar makes sure only the legal chemicals are produced. And the similarity score, even when it misses, it comes close to the prediction, the target. As you can see, it's very high, 95% or so is the similarity. So we are doing this work further. And again, this is an example of hybrid AI where here the hybrid part comes from the grammar. Okay, in eSFILES, in Vipul's presentation, you're going to see a different way of injecting first principles knowledge in the form of ontologies. But in here, Vipul did it a different way by crafting those grammatical rules, which contained a lot of the rich chemistry. Okay, to summarize, we've had different knowledge modeling approaches in chemical engineering. The first paradigm was through the work of Neil Amundsen at Minnesota, who was an applied mathematician. So Professor Amundsen brought in ideas from linear algebra and differential equations into chemical engineering to model process units like distillation columns and reactors from first principles. This is the Amundsen era of the 50s, and his disciples carried on this tradition in Wisconsin and other places. Bert Stewart Lightfoot, for example, traced their lineage to Amundsen. The next wave came through the work of Professor Roger Sargent at Imperial College, who brought in ideas from mathematical optimization, linear programming, nonlinear programming, and operations research to formalize decision-making. The first one modeled process units. The second paradigm modeled process engineers, particularly their decision-making by modeling constraints. And this is the work of Roger Sargent and his students, such as Ignacio Grossman, Art Westerberg, and others in various places. In my opinion, this is where artificial intelligence fits in as the third important paradigm. Except it's not just 5 years old. It's really started some 40 years ago through the work of Art Westerberg at Carnegie Mellon, George Stephanopoulos at MIT, and others from that era, who brought in ideas from AI, and particularly symbolic structures and symbolic AI, and combining it with numeric AI. This is data science, and that's the third paradigm. And going forward, I classify the opportunities into three categories. The easy problems, or relatively easy problems, are those with large amounts of data, which can be used with relatively easy to use machine learning models. I call them easy because people showed how to do these problems 25 years ago. In the early 90s, people demonstrated how to do these things. And even when the computers weren't powerful, when software was not easy to use, people demonstrated how to do AI. So I don't consider these things as hard, particularly hard now that we have really fast computers and very, very easy to use software. And this is already happening in the industry. The hard problems are building hybrid AI. How do you build first principles and data-driven models? How do you combine causal models? I didn't talk much about it, but this is another one. So all these require combining symbolic AI with numeric AI. And even though people demonstrated how to do these things 25 years ago, there are still some open questions. So I estimate this might take another 5 years or so to do them easily, systematically, and correctly. Harder still are building domain-specific ChatGPT-like systems. ChatGPT for pharmaceutical engineering, ChatGPT for React catalysis, and so on, or ChatGPT for process synthesis. So the eSFILES work that Professor Gani talked about, and what Vipul is going to talk about next, is along these lines. It's like a customized ChatGPT-like system for flowsheet synthesis. And this is much harder because you have to build ontologies and special purpose languages, etc. And this might take another 5 to 10 years or so. So it is this last category of problems that we are talking about today. Professor Gani gave an introduction, and Dr. Vipul Mann is going to expand on that in the next presentation. As you can see, this upper ontology is the pharma ontology, and the bottom one is the process ontology. How are these things combined with hypergraphs to address the flowsheet synthesis? And so the hybrid AI part, that is the first principles part, are all hidden here. Part of the first principles is in this materials ontology. Part of it is in the process ontology. And there are some other things that Vipul would talk about. And how these things then are used in combination with the representation, the eSFILES representation, and the hierarchical way of approaching this problem to do flowsheet synthesis and use the context and not generate meaningless flowsheets which don't make any sense, how to use the contextual information to do this properly. All that is going to be the content of the next presentation, and that Vipul would do. So I'm going to stop here and yield the floor to Dr. Vipul Mann, and all of us would stay online to take any questions after all three presentations are done. Thank you very much.
Okay, so thank you, Venkat. Vipul, do you want to say something before we start your video?
Yeah, sure, Professor. So hi, everyone. Thanks for joining and welcome to part 3 of this webinar. My name is Vipul Mann. I recently finished my PhD under the supervision of Professor Venkat Venkatasubramanian at Columbia University. And over there, I worked on the exact same topic that Prof. Venkat and Prof. Gani also mentioned, hybrid AI. How can you combine AI and domain knowledge to solve various problems in chemical engineering? Currently, I'm working as Senior Manager Biomarker Data Scientist at a US pharma company called BMS, or Bristol Myers Squibb. And again, here I'm working in the area of hybrid AI, but in the clinical trial setting or the pharmaceutical setting. So with that, we can probably get into the details of eSFILES, and we'll probably take questions in the end of the webinar. Thank you.
Okay, thank you. Hi team, please start the video. And participants, please remember to fill out the questionnaire. You have time until the end of the discussion session, but please fill out whenever you can. Please, Thai team, start the video.
So in part 3 of this webinar, I will talk about eSFILES and the multi-layer hypergraphs for process synthesis and design. The structure of my talk would be as follows. I'll first talk about the extended S-files or the eSFILES representation and cover the underlying methods such as the text-based flowsheet representation, the flowsheet hypergraphs, and the process ontologies that are used in eSFILES. And in the last part of my talk, I'll give examples of the eSFILES representation, show the superstructure and flowsheet representation using the HDA process, the cumene process, and the ethanol production process. So that's the plan for this part 3 of the webinar. And with that, let's get started. Here's an overview of the eSFILES representation. This is an approach to represent flowsheet at various different levels, given that you have a lot of information that needs to be stored for a given flowsheet. Starting at level 0, the flowsheet is represented using a text-based flowsheet representation, where only a single string is used to represent the flowsheet. At level 1, the flowsheet connectivity information is stored explicitly using a hypergraph, and that hypergraph could be given to a flowsheet generator to get multiple different alternatives of the same process. At level 2, you add some more information, and the flowsheet hypergraph now contains information about the mass and energy balance calculations, which can then be given to a process simulator number 1 to perform simple mass and energy balance calculations. And finally, at the highest level, that is level 3, the flowsheet information is represented such that it could be given to a process simulator to perform rigorous process simulations. And just I want to highlight here the fact that in order to use eSFILES, you are either required to have a process flowsheet that is either generated by the superstructure or it is specified by the user. The whole idea behind developing eSFILES was to enable hybrid AI applications in process systems engineering. Hybrid AI refers to the intersection of purely data-driven AI and process knowledge, and that is hybrid AI. And hybrid AI enables the efficient combination of process knowledge and computational methods like AI and machine learning to incorporate process context, enforce domain constraints, and ensure that the solutions that are generated by AI are feasible and not just noisy or impractical. Here are a list of examples of the various applications of eSFILES at different levels. Starting with level 1 is the sFile string, where the application of sFile strings would be the text-based flowsheet representation, flowsheet storage, sharing, and search. And text mining could be done using those with the use of appropriate context. At level 1, the flowsheet hypergraph could be used to generate process alternatives. And for this, graph-based methods could be used such that a superstructure is generated and validation checks are done appropriately. At level 2, the annotated flowsheet hypergraph could be used for process intensification, flowsheet property prediction, and so on. And this could be combined with heuristic-based graph traversal and machine learning and group contribution-based property prediction methods. And finally, at the highest level, level 3, the hypergraph connected with process ontology of the eSFILES representation could be used for flowsheet simulation and optimization. And this could be integrated with commercial simulation tools, and graphical methods for optimization could be used. So you can see that there is a lot of applications of eSFILES at different levels, and all of them could be combined with existing process knowledge while also leveraging the computational methods of AI and machine learning. And these are just a few examples, but there are many more applications that are possible by leveraging both domain knowledge and data-driven or computational methods. And doing so avoids a mismatch between process knowledge and flowsheet information. It mitigates the combinatorial explosion and complexity of the problem. And it is also a flexible and consistent way of representing sustainability and economic factors that are very important while designing and solving flowsheet synthesis problems. With that, let's get into the methods underlying the flowsheet representation. The first is a text-based flowsheet representation, which is sFILES, or the simplified flowsheet input line entry scheme. This is analogous to the SMILES representation of molecules, which, by the way, is known as simplified molecular input line entry scheme. Similar to SMILES representations, the sFILES representation also has process atoms, process bonds, and process groups, where the process atoms are analogous to atoms, process bonds are analogous to process bonds, and functional groups are analogous to process groups in flowsheet. To give you an example, consider this molecule, where here's the 2D molecular structure of that molecule, and the corresponding SMILES string for this molecule is shown here. So this SMILES string basically represents the structural information in this molecule as a single purely linear text-based representation. So this molecule is represented as C and C, parenthesis, double bond O, parenthesis, OC1, and so on. And these double bonds represent a double bond, and then the atoms are represented using this. And so you can see that the entire molecular information is represented using a linear text-based string. The analogous representation for a flow sheet would be that given a flow sheet like this, where you can see that there are two input streams to a reactor, then you have a flash, and then you have three distillation columns, and then you also have a reaction which is happening within the reactor. The equivalent of SMILES would be an eSFILES string like this shown here, where you can see that the entire flow sheet is now represented using a linear text-based representation. And this representation offers several benefits. We'll talk about that later, but this is one of the main contributions of our work, where we show that how all the information could be distilled without losing too much context and without losing too much information. So given a flow sheet like this, the first step in generating a text-based eSFILES representation is to identify the underlying process atoms and process bonds. For this flow sheet, the process atoms are as follows. So IC, IAD, these are the process atoms which correspond to the streams. Then you have the process atoms which correspond to the reactor, which is this, the flash, then three distillation columns, and the output streams, and the divider or purge here. As you can see, the different components are all represented here, which are reactors, flash, distillation column, purge or divider, inlet outlet streams, recycles, and the connections between consecutive process atoms, because something that is different from SMILES in eSFILES is that you need to represent the connection between consecutive process atoms in a flow sheet. So this is, as we saw earlier, this is a text-based flow sheet representation. And let's go through this string one by one. So the input streams are here. So you see that IAD, I indicating that it's an input stream, raw input stream is entering the process here. So it's IAD here, and then you have IC. Then you have the output streams, OAD, AD, B, and E represented here. Then you have the reactor, which is represented using the symbol R, followed by the input stream, which is ADCB, and then the output stream, which is ADCBE, or the product stream. Then you have the flash, which is indicated by the symbol F, with the top stream as AD/ADCBE as a bottom stream. Similarly, you have the purge, where in this case, since it's a divider, both the top and bottom streams are AD and AD. And finally, you also have the three distillation columns here represented using D symbol, AD as a top product, BCBE as a bottom product, and so on. And you also notice that since we have two recycle streams, so to represent recycle, there is a special symbol which is used, which is less than symbol 1 and less than 2, indicating that these are two recycle streams entering the reactor at this point, and the origination of these recycle streams are after the purge, indicated by 1 here, and after the last distillation column, indicated by 2 here. So in this way, we see that we are able to represent an entire flow sheet using a single linear text-based representation. So just like we looked at the SMILES for representing flow sheets, the question that we ask ourselves is, can a formal grammar be developed for eSFILES just like we have a grammar for the English language or for SMILES strings? So again, to answer this question, we turn to SMILES representation. So just like there is a SMILES representation, there is also a SMILES grammar, which is a natural language like grammar, similar to what we have for natural language like English, French, and so on. Formally, a grammar is basically a context-free grammar, which was formalized by Noam Chomsky in the year 1956. And the SMILES grammar is basically a finite collection of recursive rules, which can be used to assign structure to a given string. So here's an example of the SMILES grammar here. And as you can see, there are four main components of any grammar. So formally, the first main component is S, which is a designated start symbol indicating that the grammar starts over there. So smiles is a designated start symbol indicating that it is a smile string. Then you have a set of non-terminal symbols or intermediate symbols, which basically capture the underlying information or the structure of that string. In the case of smiles, that information is the underlying chemistry. So you can see that these non-terminal symbols like chain, branch atom, ring bond, bond. So all of these things are capturing some sort of structural aspects of the smile string. So these are non-terminal symbols, which are part of the grammar. Then you have a set of terminal symbols denoted by sigma, which basically correspond to the actual vocabulary and symbols used within the smiles representation. So those symbols are the small alphabet C representing a carbon atom and double bond representing a double bond. And finally, the grammar rules, which are basically a collection of A goes to B, comprises the smiles grammar. And here A could be any non-terminal symbol and B could either be a terminal symbol or a non-terminal symbol. So in this way, we have seen that the grammatical structure of any string could be come up with if these four set of symbols and rules could be defined. And like I mentioned, Smiles grammar could be used for assigning structure to a smile string or a molecule. And with that, let's take a look at the eSFILES grammar that we developed from scratch. The developed formal eSFILES grammar can be used to automatically parse eSFILE strings. It can be used for performing automated syntax checking, because if you're given as eSFILE string, you would want to automatically check whether the eSFILE string is syntactically valid or not. Then you can use this eSFILES grammar to assign structure to eSFILES string. And finally, it can be used for inferring connectivity information automatically. So with these applications, we thought of developing the eSFILES grammar, and this is how the eSFILE grammar looks like. So it looks very similar to the Smiles grammar. And again, you can see that you have a start symbol, eSFILES, which indicates that something is part of the eSFILES representation. Then you have a set of non-terminal symbols like PA, PG, which basically indicate a process atom, process group, an equipment, a distillation column, top stream, bottom stream, and so on. Then you have a set of terminal symbols, which basically correspond to the actual vocabulary in the eSFILES string. So you have A, B, C, D, E, which can correspond to any material. And then you have reactant marks indicating if something is a reactant, or distillation column, inlet streams, outlet streams, and so on. And finally, the collection of rules of the form A goes to B is comprises the eSFILES grammar. So this grammar can be used, like I mentioned, for performing all of these tasks. And our primary use case of the eSFILES grammar is to assign structure to eSFILE strings and to infer connectivity information automatically. But before we talk about that, let's take an example of how this grammar could be used to assign structure to an eSFILE string. Again, consider a very simple system where you have a reactive flash, meaning that A is the input and B and C are the output, meaning that A undergoes a reaction to produce B and C, and they are separated using a flash with B and C as the output. The eSFILE string for this simplified flow sheet would be as follows. You have the input IA, then a reactor where the inlet is A and the outlet, the product stream is BC, which are then separated and exit the flow sheet as OB and OC, O indicating that they are outlet streams. When we use this eSFILES grammar to parse this eSFILE string, the following grammar tree is obtained. So this grammar tree basically shows how the eSFILES grammar rules could be systematically applied in order to get this tree, in order to get the underlying structure behind the eSFILES string. For example, we start at the very top and apply rule number 1, which says that the eSFILES string goes to a PG, which is a process group. Then from the PG, you apply again rule number 2, 2 times. Rule number 2 says that a PG can be broken down into a process atom and a process group. And the same rule is applied again at this node to again get a process atom and a process group. On this process atom again, rule number 4 is applied, which says that a process atom is represented as BRAC1 or parenthesis 1, and followed by a process atom, and then followed by another parenthesis. Then rule number 5 is applied, which is saying that the process atom goes to an equipment. Then rule number 10 is applied, which says that the equipment is a reactor. Then rule number 13 is applied, which says that a reactor is represented using a reactant mark, a reactant, backslash, and product. And then the reactant mark basically is obtained by applying rule number 29, which says that the reactant mark is actually an R symbol. Then rule number 21 is applied to get the material as A, and so on. So in this way, we can see that the grammar rules could be systematically applied to get the eSFILES string symbols. And as you can see, this grammar tree is a lot more informative than just looking at the eSFILES string. And this grammar tree captures the context, which is very important for solving any of the flowsheet related problems. And that context defines the problem and the problem solution space. So the grammar, eSFILES grammar, not only does this, but also captures the contextual information, which is very important for solving such problems. Moving on to flowsheet hypergraph. The second method that I'm going to talk about is representing a flowsheet as a hypergraph. So we represent the flowsheet connectivity information as a numerical graph-based representation, where the streams are represented as vertices or nodes, and the unit operations are represented as hyper edges. Recall that a hyper edge is different from a directed edge in the sense that a hyper edge can connect any number of arbitrary number of nodes together and not just two. For example, here A is connected to C using a directed edge and B is connected to C using a directed edge. So in total, there are two directed edges which are required to connect A, B, and C together. Whereas here you see that there is a single hyperedge which connects both A, B, and C together. So this is the hyperedge idea that we use to represent a process flow sheet. So again, given the same process here, the flow sheet hypergraph looks something like this. So you can see that there are again a couple of components here that we need to pay attention to. The first component is the set of vertices, which are C, AD, CBE, AD, CBE, CE, CEP, and so on. So these are basically all the streams underlying this process. So these are all the vertices. The process atoms are represented as hyperedges. So these are the hyperedges that we have: R1, F1, D1, D2, D3, and PRG. So basically this hyperedge R1 says that it is connecting AD and C together to AD-CBE, and this R1 is nothing but the reactor. Similarly, the flash is represented using this hyperedge F1, which is connecting AD-CBE here to AD and AD-CBE. Similarly, you have hyperedges for D1, D2, and D3. And also you have recycle streams, which indicate that they exit the distillation column here and re-enter the reactor at this point. And the third component is the node edge row labels, because it is important that we capture the directionality of streams. So we can either use a directed edge or hyperedge to represent the directionality, or we could also use node edge labels such as input and output or in and out, which indicates that something is going into a process atom or something is coming out of a process atom. The other possible annotations are top, bottom, recycle, because remember that we also have top and bottom annotations for something like distillation columns or flash and so on. So this hypergraph not only can represent directionality, but can also represent additional information specific to a node edge pair with the help of these annotations. Finally, coming to the third method that I'm going to talk about is the process ontology. So recall that an ontology organizes information hierarchically in the form of class subclass relationships. Classes represent a broader type of objects. Attributes capture the relationships between different classes, and the instances represent fundamental objects. And one of the main value proposition of ontologies is that they preserve the semantics and they offer an efficient knowledge representation framework. Here's an example of a process of an example of an ontology typically used in the pharmaceutical manufacturing area. So the main class is a drug manufacturing class, which has 4 main subclasses: design specifications, material properties, risk grids, and materials. And each of these have further subclasses such as drug API, drug product, excipients, and so on. And you can see that hierarchically, these subclasses capture information in an efficient manner. For the process ontology, we developed an ontology which has the process atom as a main class and 2 main subclasses, operation and design. The whole idea is to be able to represent information related to a flow sheet that is used for operation and design aspects of simulating or generating the flow sheet. The operation class has a subclass called streams, which has 2 subclasses called input and output. The input class will contain all the information related to the input streams entering the process atom, such as the temperature, pressure, the phase, composition, rate, and so on. And similarly, the output would talk about the process atom exiting streams. The design's main subclass will capture information related to the design aspects of a given process atom. For instance, the reactor subclass will have properties like the type of the reactor, the reaction stoichiometry, the reaction ID, what kind of reaction model is used, and the conversion rates. Similarly, the distillation column would have information on the distillation design aspects such as the number of trays, condenser duty, reboiler duty, and so on. In this way, we can see that we can really capture a lot of information that is used to represent a process in a completely context-aware manner. And this context is organized hierarchically in the form of class, subclass relationships. While this is a simple way of representing a very complex amount of information for a given process atom, there are other possibilities like OntoCape or some of the standard ontologies which could also be used to represent this information. But the idea is still the same, that we should be representing information hierarchically as class subclass relationships. But we have covered the underlying methods of eSFILES. Let's take an example starting with the HDA process. So as covered by Prof. Rafiqul Gani in part 1 of this webinar, given a process context and the problem specification, the first step is to generate a superstructure of alternatives. For the HDA process, this is the superstructure of alternatives that we have. And again, as covered in part 1 of this webinar, the superstructure can also be represented using a simple text-based representation. So you can see that you have 2 input streams and a process atom. Then you have 2 recycle streams, and then you have a series of process atoms. And the J and K here basically represent the different alternatives that are possible given this process context and they were given this problem specification. Based on this superstructure, there are 10 feasible flow sheets which are possible, and the S files string for these flow sheets are shown here. And like I mentioned, each of these 10 alternatives could be represented using eSFILES representation at 4 different levels. So I'm going to take one of these examples, one of these possible flow sheets, and then represent that at 4 different levels, starting from level 0, 1, 2, 3. So here's the level 0 text-based representation for one of the alternatives of the HDA process. This is the same example that we saw earlier while I was motivating the level 0 representation for eSFILES. So you can see that the flow sheet is broken down into process atoms and process bonds, where the process atoms represent unit operations, process streams are represented as process bonds, and recycles in the flow sheet are represented by numbers like 1 here and 2 here, and special symbols less than indicating at what point the recycle streams are entering the process. So that is level 1 representation. At level 2, that is level 0 representation. At level 1, we want to represent the flow sheet as a hypergraph because we want to facilitate the use of simple mass balance models and explicitly represent the connectivity information in a given flow sheet. So that connectivity information is represented using a hypergraph, and this allows for graph-based methods to be directly applied on the flow sheet. And here is the level 1 hypergraph-based representation. So you can see that the nodes in blue here represent the input nodes. So AD and C are raw input streams to the process. Then you have reactor represented as a hyperedge R1, which has output as ADCPE. Then you have flash F1, D1, D2, D3, and PRG purge representing the different process atoms. The recycle streams are shown in red here, and the output process bonds are shown in yellow here. And everything else, the white process nodes are basically the intermediate process bonds, which represent the intermediate streams. So in this way, we can say that not only the flowsheet hypergraph is able to visualize the process, but it can also be used with graph-based methods because it's a numeric representation of flowsheet, and we can directly perform computations using this graph. And that is one of the benefits of using the flowsheet hypergraph at level 1 as opposed to a simple process flow diagram, which lacks some of the contextual information. At level 2, we want to capture some more information so that we can facilitate the use of mass and energy balance methods. So in this case, we need to capture not only the connectivity information, but also the flowsheet context. And that context corresponds to the material and energy balance, the reaction stoichiometry information, the conversion factor, the split fraction and divider fraction, and so on. So in order to capture that contextual information, we have to use something called node edge labels. So node edge labels basically mean that for a given node and for a given edge, the process atom and the process bond will have some annotations which capture this context. For example, for this input stream C and for this process atom reactor, we have an annotation called MC, which indicates a component flow rate for stream C. Similarly, we have MAD for AD stream, which indicates a component flow rate for stream AD. For this reactor, we have the conversion factor X1, the stoichiometric coefficients alpha 1 as the node edge annotations. Similarly, for something like flash, we have the split fraction. For distillation, we have the split fraction again, and so on. For energy balance, we track the temperature or pressure of a given stream entering or leaving the process, again using node edge labels. So this stream, in the context of this process atom, will have an annotation E indicating the temperature or pressure, and this E is basically captured at each intersection of a given process atom and a given process bond so that energy balance could be performed. So in this way, we can use the level 2 annotated flowsheet hypergraph representation to perform simple mass and energy balance calculations. Finally, at level 3, we have the hypergraph connected with process ontology. And the whole idea here is to facilitate the use of rigorous simulation models. And for this, obviously, in order to perform rigorous simulations, we need a lot more information that needs to be captured. And that was the reason we developed the process ontology here, where you have the process atom at the very top, and then you're capturing the information related to operation and design aspects with the help of subclasses like input-output streams, and the design aspects correspond to each of the different kinds of process atoms like reactor, distillation columns, and so on. So this process ontology is connected to the process atom, and each process atom will have an instantiated version of this ontology connected, meaning that for reactor R1, you will have the input stream, the output stream, and the details of the input stream populated in the ontology. And again, for the same reactor ontology, you will have the type of the reactor, the reaction stoichiometry, the reaction ID, and so on, also populated as part of the same instantiated ontology. So we can see that with the help of this ontology, which is instantiated by filling out all the details, the reactor information is efficiently organized. The same thing would be done for rest of the process atoms like the distillation column D1, where you are capturing all the information pertaining to distillation column design aspects and distillation column operation aspects and storing that here. So we can see that this process ontology connected with the hypergraph can capture all the information that is needed to perform rigorous simulations. And please note that this data can be generated by available design methods, which can be passed to any process simulator or commercial simulator through an appropriate interface. I'm going to talk about the interface also in the later part of my talk. So now that we have seen the 4 levels, level 0, 1, 2, and 3 for the HDA process, let's also take an example of the QMean process. So again, similar to the previous example, given a process context and a problem specification, the first step is to generate a superstructure of alternatives. For the QMean process, this is the process context and the problem specification. And two of the feasible alternatives are as follows. The first flowsheet alternative is a 1-reactor QMean process. So you see that it has 2 inputs, benzene and propylene, and it goes to a reactor followed by a flash and 2 distillation columns. And the second alternative is a 2-reactor QMean process where you have 1 reactor here and other reactor here, and then you have 3 distillation columns, and this is the process. Now again, each of these alternatives could be represented using the eSFILES representation at 4 levels. And for the purpose of this example, I will focus on representing this flow sheet using the 4 levels of eSFILES. So again, given the process flow sheet, the first step is to break it down into different process atoms and process groups, and then write down the eSFILES level 0 representation. So you can notice that again, the input is represented as IA, then the reactor is represented as the R symbol followed by reactant product, then IB is the second input stream, and then you have another reactor represented here, and then you have the recycle streams 1 and 2 coming out of the purge and the distillation column. So this is the first recycle stream, and this is the second recycle stream. And the same thing is shown schematically here. And this is again connected to Prof. Gani's part 1 of this webinar, where he talked about the graphical representation of eSFILES in the form of process bonds and process atoms. So this is what is needed to generate level 1, level 0 of the eSFILES representation. At level 1, the same information is represented using a flowsheet hypergraph, where you, again, as earlier, you would see that there are 2 input streams, then there are 2 output streams, then there are 3 recycle streams that are being recycled, and then you have the reactor 1 here, and the second reactor is here. And as you go further, if you have more information about the mass and energy balance, then level 2 could be generated by adding annotations for each of these node edge pairs, just like we saw for the HDA process. And at level 3, if you have further information and if you would want to perform rigorous process simulation, then the process ontology should be populated for each of these process atoms before giving it to a commercial simulator to perform rigorous process simulations. Finally, here's one more example for the ethanol production process. Given a flow sheet like this for the ethanol production process, here you have a reactor, a flash, then 2 dewatering columns and a finishing column and purge, and also an absorber. The level 0 representation is this. Again, notice that the input is BEF, then you have a reactor, then another input A, and then you have the distillation column, the absorber, and all of these things. So this is level 0 representation. And at level 1, like I mentioned earlier, we again represent the entire flow sheet using a flow sheet hypergraph with different kinds of nodes and different kinds of process atoms or hyperedges. And again, we see that the eSFILES representation is flexible, not only from a visual representation standpoint, but we can also see that it can handle different levels of complexities and different kinds of process atoms and different kinds of connections between them very efficiently. And just like for the QMean process, if you have more information on the mass and energy balance calculations, and if you also would like to generate rigorous process simulation data, then level 2 and level 3 can also be populated using the same set of concepts for eSFILES. Now that we have covered a couple of examples, starting with HDA process, then QMean process, then ethanol production process, let's talk about the prototype software that we have developed. So the eSFILES representation is not just a proof of concept. We have a fully automated conversion of eSFILES representation across various levels, and we have a prototype software for that. And this software is characterized by a couple of modules. The first module is a sFILES grammar, which is basically a formal set of rules that define the formal structure of text-based sFILES representation. And this is used to check the consistency and accuracy of flowsheet representations. The second set of module is the inference algorithms, which is basically used to identify the process streams, the process atoms, and the stream compositions. And it is a suite of algorithms to also infer the connectivity information between the process atoms and process bonds. And for example, in order to generate something at level 0, the input to the software would be the set of process atoms and the connectivity through process bonds, and the output would be the eSFILES string. At level 1, the input is the eSFILES string along with the eSFILES grammar and the inference algorithms. And the task here is to represent connectivity information, and the output from that software is a flowsheet hypergraph. At level 2, the flowsheet hypergraph is given as input along with the equipment parameters for simple models and the chemical identities, because now you need to know what does each chemical represent. And then the output would be the annotated flowsheet hypergraph, which can be used to perform mass balance calculations with simple models and so on. And finally, at level 3, the input would be the annotated flowsheet hypergraph, the design and operation parameters and process ontology. And the output would be the annotated flowsheet hypergraph connected to process ontology, which can now be used to perform rigorous flowsheet simulations by connecting that to a commercial software. Here's some more details on the prototype software. So you have the 4 levels of eSFILES, that is level 0, 1, 2, and 3. And at level 3, you would have all the information that is required to rigorously simulate a flowsheet. And the connection is made to rigorous simulation softwares like commercial softwares using a keyword input file, which basically maps each of the keywords in the process ontology with each of the keywords in the process simulator. And this is an example of that keyword simulation file or keyword input file, which is used by commercial simulators like Aviva or ProCFD and so on. So this serves as the bridge between the eSFILES representation and the process simulator. And once you have this bridge, you can perform rigorous simulation, generate a simulation report, add some more data, and use process analysis tools, and further fine-tune the process, further optimize the process, and finally also incorporate some of the sustainability and other factors of interest. And since we have this bridge, we can also rank and perform a feasibility check on the flowsheet alternatives. We can generate a flowsheet alternatives and represent the superstructure, and we can also perform rigorous simulations like we saw here in this pipeline. So in summary, we have seen that the very first step is to define the problem, and along with that, we also need to define the flowsheet context, because without defining the flowsheet context, the problem specification is incomplete, and there are millions of possibilities or thousands of possibilities for solving the same problem. So the problem specification and flowsheet context definition is the very first step. Once you have that, you would generate a superstructure so that you have a list of alternatives that fit within the problem specification and the flowsheet context. And once that superstructure is generated, a list of feasible or desirable flow sheets could be found out, could be enlisted. And from those flow sheets, each of the individual alternatives could be represented using the eSFILES representation at 4 different levels. For example, if a flow sheet is of interest based on the superstructure that is generated, these 4 different levels would be generated for that flow sheet, which will contain different levels of granularity of information at each level. Again, level 0 will be a purely text-based representation, which will represent the entire flow sheet like this, similar to smile strings for molecules. And then this level 0 representation will be combined with the eSFILES grammar and syntax rules to get level 1 flowsheet representation, which is a flowsheet hypergraph. And this explicitly represents the flowsheet connectivity information. Now, this level 1 can be combined with some of the material and energy balance calculations to get a flowsheet that also contains the material and energy balance information along with the connectivity information. And that is achieved using an annotated flowsheet hypergraph. And you can see that these are the annotations for each of the process atom and process bond pairs. And finally, this level 2 can be combined with some design and operation parameters to get a flowsheet representation that is ready for simulation. And that representation is basically a hypergraph connected with process ontology, where each of the process atoms has an instantiated ontology containing all the design and operation parameters of interest. So this was the eSFILES representation. And thank you very much for your attention. And I look forward to answering your questions along with Prof. Rafiqul Gani and Prof. Venkat. Thank you.
Okay, so thank you very much for all the three presentations. One thing to the participants, please try to access the questionnaire and fill out the questionnaire. It is very important for us. The questionnaire is still going to be open until we finish the discussion session. And now the floor is open for questions. I've noticed that there were one or two questions on the chat box, but these were already discussed in the chat box. If you have any questions, please show your hand, and we will ask you to read out your question. Are there any questions? There was a question on the chat box that was not answered, so I will read it out for you. This is from Wang Tongyu, and he writes, there was a discussion on self-driving algorithm training. In the beginning, Tesla also set some rules on the driving, but recently Tesla started to train the algorithms only based on the data, even without the radar sensors. And then he continues, at this time, process industry is still struggling, integrate domain knowledge into process synthesis, very similar to the scenario of setting rules to the self-driving. We cannot get rid of the domain knowledge and train the algorithm for now. Is it because we don't have enough industry process data, or we have other reasons? I guess, Venkat, you will answer this.
Yes, happy to. Good question. Thank you very much. Yes, as you suspected, we don't have that much data for many problems in chemical engineering. We certainly have more data now than we did 10 years ago, but it is nowhere near the amount of data that is generated in computer vision or natural language processing or game playing programs. For example, going back to the Tesla example, with millions of cars, Tesla cars out there already, and several years over, at least going back by roughly maybe 10 years. And all the data is gathered by Tesla. That is an enormous amount of data that you can, and also practical data. This is data that comes from people driving in roads under various conditions, etc. So under those conditions, I can imagine the rules or heuristics that people might have come up with initially, may not be needed anymore because you have so much data to map the entire space. So you could have a purely data-driven approach. Whereas we don't have that kind of abundancy of data in many chemical engineering problems, including process synthesis related ones. And as a result, the domain knowledge is still useful and, in fact, essential because you don't have as much data. Number two, self-driving cars, basically they are solving real-time computer vision problems in navigating, okay? And so there are no fundamental laws governing that. There is no conservation of cars. Well, I suppose in a way there is, a car doesn't simply disappear, it makes a turn and then leaves the highway or something. But what I'm getting at is there are no fundamental laws of physics or chemistry which govern computer vision. Whereas chemical plants are governed by conservation of momentum, mass, energy, you have VLE equations and so on. So our space is a lot more constrained that way. And we know that. And so we can use that, we can leverage that to reduce the search space for the automated system. And that, again, would require less data to train. So in chemi problems, since we have less data compared to computer vision, the way to handle that is to inject domain knowledge wherever appropriate, and then the data problem is not as concerning anymore. Thank you.
Okay. I will read out one question from Gabriel Hernandez Morales that Vipul has already answered in the chat box, but it's better Vipul also answer it so others can hear it. So his question is, since the S-file follow the same grammatical rules as SMILES, what are the benefits and advantages of using S-files?
Yeah, so I can answer again. So the whole idea is behind S-files is to come up with a alternative or analogous representation for flow sheets similar to SMILES. So remember that SMILES can really capture a lot of information about a given molecule structure using a simple text-based representation. And what we did with S-files, which is eSFILES level 0, the base level of eSFILES, is to have a very high-level information of a given flow sheet in the form of a text-based representation. So that is the only purpose of having that text-based string. Now, when you combine that text-based string with grammar rules, then you can really perform inferencing on the text-based string. You can find out what are the different process atoms, what are different connections, and so on. So that is the the whole purpose behind developing a text-based representation like S-files or eSFILES level 0. And the other thing is that the limitation, you asked about limitation. The limitation is that you do not obviously have all the information in that text-based S-files representation. So that is why we have levels 1, 2, and 3, so that you can add more and more information depending on how you would want to use that representation, what problem you're trying to solve.
Okay. There is a lot of questions from Gabriel, but I want to see whether some other people want to ask questions first. Are there somebody else interested to ask questions? Okay, there is one more here.
Yes, I would like to ask a question.
Good.
Yeah, I just want to know, my name is Emmanuel. I just want to ask whether this platform is commercially available and what are the requirements for having the computer platform, to be used, as well as what's the what's the speed of a typical simulation, using these connected platforms?
If I understand your question correctly, you're asking whether the software is available for use by industry or for academia. Is that it?
Yes.
Maybe I can answer it for all of us. If we are talking about the sustainable process design, we do have a software that we give out for educational purposes. We need to make an agreement. Remember that you mentioned also simulator. The tool connects to the simulator. You need to have your simulator. But all these other things, it depends on if you follow all the 12 steps according to the manual. Maybe you would need 1 week to solve the problem. It could be solved as fast as maybe an hour or 2 if all the data are available. But it does not include the simulation time because the simulator is an external tool. And any academics who are interested can contact us. With respect to the AI tools that Venkat mentioned, Venkat can answer. With respect to the prototype that Vipul has mentioned, we are trying to incorporate that into the software that I mentioned.
Right. The prototype that Vipul developed is it's still under development, and so we're not making it available publicly yet. There's also work going on extending its capabilities and so on. So we have limited engagements with various groups, like Professor Gani mentioned, and other than that, presumably it will be made available, but we are not there yet.
Okay, here is an interesting question from Troy Gustke. He is asking, what is the vision for incorporating LLM into enhancing the human aspect of ProCFD software? Do you think that the current LLM models are advanced enough to help? Venkat or Vipul, do you want to try?
I've been talking a lot, so let me ask people to handle.
Yeah, sure. I think this is for sure an interesting question that, how can we integrate LLMs into ProCFD or simulation software? So, I see that the integration can be in two ways. The first bit is, not letting the LLM solve an actual chemical engineering problem, but just focus on, assisting what is being done by ProCFD. For example, the user can write down the problem specification, some more details in the context, and the LLM can probably understand the context and try to map that into a mathematical extract the relevant information so that that information can be given to a process simulator. So if the LLM is not touching any of the ProCFD internal simulation stuff, then I think LLM is easy to integrate. But then when you talk about using LLMs for the second kind of integration, where you would want to solve the simulation and you would want to solve the flow sheet problems also using LLMs, then I think there would be a bit of challenge. And I don't think that is very easy problem to solve, or even a medium, moderate difficulty problem to solve. It's an extremely difficult problem. And that was the whole basis behind the eSFILES work, that, we do not want to do purely LLM-like simulation or purely LLM-like approach to solving chemical engineering problems.
Yes, here I would just add to what Vipul has said. The process simulation, we do not think the LLM can solve those kind of problems at this moment, at least. So we need to generate enough data which will then formulate the problems that the rigorous simulators models in the commercial simulators that they can be run, and we can get those answers. I do not think LLM models at this moment can do those rigorous simulations that process simulators have, and industry also are not interested in those kind of LLM models, but maybe in the future. There are several other questions, but I see one other related question from Ivat Caballero. He says, which commercial process simulation do you consider can be useful for hybrid AI modeling? I see from slides you use a lot of AVEVA Pro 2. There is any advantage in the syntax to use these commercial tools? With respect to the AVEVA Pro 2 simulator, this is because at least with respect to ProCFD, all the tests have been done with AVEVA Pro 2 simulator and the link to Pro 2 simulator, because we have this simulator with us and we are able to, we have the license to use them. So that's why the examples were made with Pro 2. But in principle, we can do the same for any other commercial simulator. As Vipul had pointed out, the input information for all these simulators are similar. We just need to see what is the form or the interface that is necessary. And then any of the simulators can be used. So for us, it doesn't matter which simulator, we will provide the data that is needed. The Aviva Pro 2 was used because we do have it for testing purposes. Then let's see some questions. If anybody has a question, even if you have it in the chat box, you can show your hand and we will ask you to ask the question. Otherwise, it's difficult to read all of them in here. So one question for Venkat here, also from Gabrielle. In the results shown from the adjustment of different equations using the AI Darwin method, some exponents have fractional values. What is the physical meaning?
Well, that really depends on the context, right? That's where the underlying physics and chemistry would matter. So for example, certain things may go as the square root of, say, temperature or something like that. So, and that has a fractional exponent. And so one has to get to the physics or the underlying phenomena which is driving that process. And so that's where the second half of that system, which I didn't talk about, I only mentioned it in passing, Megan, comes into picture. The mechanistic explanation generator would take the AI Darwin model and then relate it to fundamental principles and then explain the mechanisms and then justify why this equation makes sense. Now, that part I didn't talk about. We have written about it. It's mentioned in the papers I cited in those slides. So you might want to take a look at them.
Okay. There is another question from Manuel Gomez Ochoa. He's asking regarding the innovative steps for the design of sustainable processes. Could one use the ontology approach to determine whether a section of the process can be replaced by an intensified technology, for example, RD, dividing wall column, reactive distillation, and so on, using AI? I think it probably, I should answer it and maybe Vipul can add or Venkat can add. At this moment, we have developed the domain knowledge that tells us whether from just looking at the process and some of the rules or questions that we have put, whether any of those innovative options can be used or not. So that is already there. We need to develop, just like Vipul has shown, the ontology for up to level 3. We need to add a level 4, which will be the intensification and the innovation options, and what kind of data would be needed and how those data would be organized. But we do have the process groups now for this kind of innovative solutions. And we do have the, you can say, the rules plus the numerics that are needed for to apply the AI. But we do not have a prototype software yet. It's more going manually from one data set to another data set. Do you want to add anything to this, people, or Venkat?
So yeah, maybe I can add something. So so if you look at the grammar, or if you look at the eSFILES representation or the hypergraph, you can see that we have a concept of process groups. So by definition, in principle, we can really combine process atoms, and so that is one of the main premises of process intensification, that whether you can combine process atoms together and make the process more efficient and so on. So in theory, we have the tools and techniques in place to perform process intensification as well going forward. And I think that is one of the applications that we are thinking for eSFILES as future work.
Thank you. There is another question from Saripali. Are we getting the most feasible process flow sheet and optimal process parameters only? Is there the consideration of equipment specification like volume of reactor, heat transfer area required, and other aspects in finding the optimal process design? So here I would say what we have highlighted is the process synthesis aspects and the first simulation of the promising flow sheets. We did not highlight the equipment design and the process design aspects that give the economics and so on. But these tools are already in place and they are integrated after the process simulation is done and a simulation report is made. With that, the rest of the calculations would be done and a volume of the reactor, heat transfer area would be determined to obtain the cost and so on. So those features are there. They are not automated, but they're interactive. Then let me see. I don't see any new questions. If I'm not seeing your questions, please show your hand and ask the question. I can ask a follow-up question from Tang. Oh, sorry. Yes, I found the question. Following this answer that Venkat gave, if we want to train ChatGPT for chemical engineering and the domain knowledge mostly comes from the published papers or textbooks, if the software is going to be commercialized, may I know how to solve the IP conflicts?
Yes, the IP conflict is an important one. One can first start with material that's already in the public domain. And very much like how GPT itself was trained. As you know, ChatGPT, GPT-1, which was developed around 2017 or so, that was trained on 4.5 billion tokens, let's say approximately words. 4.5 billion words from data available, from documents available on the internet. Clearly, they didn't pay much attention to the IP concerns there, or they used things which were publicly available. GPT 3.5 was trained on 100 times larger training data, about 500 billion tokens, and that was 2021, 22, and that was almost everything that was available on the internet in public domain. And so, and we don't have numbers for GPT-4 or 4.0, which came out recently. So there is information there that we can identify and get around the IP issues. But unlike we'll have to deal with equations and so on. So typically ChatGPT like systems don't do that well yet on mathy material, and so that will certainly change in the coming years. But and for us, that is a big problem, right? So in chemical engineering and other scientific and engineering fields, there's a lot of math involved, and that math, in fact, has to be understood in the context of the process or the phenomena that is associated with those equations, etc. So it makes it a lot trickier. It's not as easy. That's why you need ontologies and so on to guide the learning and also the decision making. Ontologies are not that much needed in day-to-day conversation kind of things. You can infer the ontology just from the conversations and then build a model, which is what GPT does. But you do need ontologies for technical domains, and that requires a lot more work.
Okay. Are there questions again from anybody? There is just a comment by Eduardo Funcia. He asked, they said that the recorded videos will be placed on the PhD for Speed YouTube channel. Yes, I can confirm that they will be placed on the YouTube channel, as well as if you wanted to get a copy of the presentation file in the form of a PDF file, they can be downloaded from the PhD for Speed website. These files are already available. And I will remind for those who are still online, please fill out the questionnaire. It's very important for us. And then we can ask any more questions. If Gabriel is here, you can ask your question if you want. I think I did not read all your questions.
Can I ask you a question?
Yes, sure.
Oh, hi. Thank you very much for this seminar. I have learned a lot from the three of you. This is very inspiring one. And thanks for the answer from Venkat about my question about self-driving and just the last one about IP protection. And I have one more question to Venkat. So we were seeing that AI training for LLM or any model is like a black box, but actually in history, those empirical equations in chemical engineering is also like a black box. So the first question would be, is there any difference between the empirical equations and the AI model? Or what's the differences between these two? Regarding to the black box. And the other one is that because our computing power is increasing and we have better algorithm as well, is there any possibility to solve those complex empirical equations to make it into a simpler version? For example, like Newton's law. Is there any possibility to make it into another new direction in research?
Right.
That's all the questions. Yeah.
Right. There are at least a couple of different questions involved there, and I'll try to answer them in that sequence. Your question regarding empirical approaches or the empirical origins of chemical engineering, for example, and that is true. Empirical equations are like black box models, and that's why people were unhappy about them then, as we are about black box models now. I have written in my papers that the current state of machine learning is like that of alchemy, 300-400 years ago, maybe 500 years ago. So, in the days of alchemy, people kind of knew what to do to produce different things. They would mix this and that. And when they did that and heated it and then cooled it, they got this. They had the recipe. They didn't know why that recipe worked, but they had an empirical understanding of the phenomena. So that's how alchemy started. And then alchemy graduated to chemistry. Then chemistry became chemical engineering. Okay, so the current machine learning status, in my opinion, is at the state of alchemy. We have a bunch of algorithms like backprop and transformers, reinforcement learning. You know, we know a bunch of techniques, and we know how to kludge these techniques together to get the results done. Okay, for example, you know, given a problem, can we specify how many hidden layers should be there in the neural network? Does it need 1, 2, 100? How many hidden neurons should be there in each layer? 100, 1,000, million? No idea. It's purely determined by trial and error. Okay, so we cannot design a neural network from first principles right now.
Oh, yeah.
You simply try different things. What is the first principles understanding of neural networks? We have first principles understanding of our process flow sheets, as Professor Gani explained. We don't, 150 years ago in chemical engineering, people guessed the flow sheet. They said, okay, looks like we will do the reaction. Let's mix these things up. How much material A should be added? How much material B should be added? To what temperature should it be heated? At what pressure should we maintain it? No idea. Let's do it. Let's see whether it works. Sometimes it exploded and killed people. And then slowly, as the understanding grew, first principles based design came along. And now, we don't guess flow sheets anymore. We don't need autocomplete to do flow sheet synthesis. We know how to do flow sheet synthesis. People have been doing this for, at least based on mathematical models, combined with empirical or heuristic understanding along the lines of Douglas that Professor Gani mentioned, at least for 50 years. Okay, so in a similar way, where is the first principles understanding of the neural networks? Can I design the neural network from first principles? The answer today is no. And that is because it is like alchemy. Now machine learning has to go from alchemy to chemistry and then to chemical engineering. And that might happen in the next 10 to 20 years because things are happening very fast. In chemical engineering, the transition happened over 100 years. Machine learning, that might happen over 20 years because lots of people are working. There's a lot of money involved. A lot of resources are being thrown at it. And the failed experiment typically doesn't kill people. In chemical engineering, failed experiment can explode and kill people. Here, if your algorithm fails, you don't get a fit. Your model is wrong and it doesn't converge quickly, and so on. Hopefully, it doesn't kill people. All right. So we will. So that's the empiricism. Is your point is well taken. It is, these things are similar. Going forward, just as we got first principles to design both chemical products and chemical systems like flow sheets, we need to discover those for understanding for deep neural networks and transformers and so on. See, the transformer architecture and attention was guessed. What is the first principles basis of that? And, it's transformers have multi-head attentions. How many heads do you need? Okay, and I suspect most of these current LLMs are over-designed and over-parameterized. Take GPT 3.5, which is behind ChatGPT. It has 175 billion parameters, trained on 540 billion tokens. I would guess that that is an over-design. We may discover maybe in 5 years, maybe even less than that, maybe in a couple of years, that GPT 3.5 capability can be achieved with not 175 billion parameters, maybe 1/10 the size. Maybe 10 to 20 billion parameters may be adequate. And because there will be, they'll discover these systems are, massively over-designed. Not just 2x, I suspect they're probably 10x over-designed and maybe even 100x. Again, I don't know. I'm just speculating a little bit, but I'm fairly confident they're all over-designed because that's what people do. You don't know how much you need. You throw as big a network as you can create that your processors would allow. And so you go to the biggest and then train it. And so a lot of these things need to be answered, mostly by computer scientists, but the field is open now. Anyone can work on these problems, including chemical engineers. We have the tools, we have the understanding of design. In some sense, we understand design better than computer scientists because that's what we do. We've been designing chemical plants for centuries. And design is a well-developed field, subfield, process systems engineering in general, and design in particular is a well-developed field in chemical and mechanical engineering, and where we deal with all kinds of processes, all kinds of transformations, solid to liquid to gas, phase transformations. We have distillation columns, reactions where new compounds are formed. So chemical engineering is a much richer domain than mechanical or electrical engineering or computer science for phenomena. So I would, in fact, guess that if we can master enough AI, we can be better AI system designers than even computer scientists, because we come with a much richer set of tools to address these things. So and these are the exciting things one can work on going forward.
Okay,
These are what
Venkat,
I call as the hard problem, hard and harder problems.
I will stop you there, sorry. And
Yeah.
take the last question. Can the global features of the hypergraph be used to examine flow sheets using the energy consumption index, sustainability matrix as criteria? At what level can these features be included? I think Vipul could have answered this very well, but he has to go to his work. So I will try to answer it in the sense that these are already included in the method that I showed. We do take into account the numeric values of the energy consumption, sustainability metrics, all of these at different levels in order to identify the promising flow sheets. What we do not have at this moment is that these are not included in the hypergraph information or the ontology. This is some ongoing work that needs to be done so that all of these things can be integrated. But the domain knowledge and the necessary steps are already being done at this moment. And I think before I finish, I would like to thank the Thai team. Can you please show yourself, the Thai team members, so people can see you? You open the video. The Thai team members. Okay, it looks like it's not possible to see them, but thank you very much, the Thai team, for organizing this webinar. Are there any last-minute questions? So there are no last-minute questions. So then I would say thank you very much for participating in this webinar. We hope you found it useful and interesting. And in future, look out for the next webinar. We are thinking that we might do a similar one with respect to product design, sustainable product design with AI and all these things. So all the best and thank you very much.